Good morning. So today, do we again have architects and mathematicians and geometers? So if we are mixed, my proposal for today is the first part. So I give two talks today. The first talk will be very elementary, and it is mainly dedicated to architects. So it is in fact taken from a chapter of our book on architectural geometry, and I will talk about developable surfaces, because I have seen here various people working in this direction. In this working group, this also came up. And then in the second talk, again, it is not really hard mathematics, but it is more mathematical, yeah? And then we will talk about things that are slightly more advanced. Yeah? So let us get started. We will talk today about, this is still not perfect, maybe we can you see it? You can see it, okay. And you can hear me also? Okay. Developable surfaces and unfoldings. The motivation for architecture we have already heard yesterday. Depending on the material, a developable surface will have yes, I think it's better. Yeah, thank you. And here, yeah. Here we still have some light. Nah. Nah. Nah, it doesn't matter. The sun position will change, and also this will change here. Oh, very good, very good. So, I think the application we discussed yesterday, and I remind you, a developable surface is a surface which can be unfolded, developed into the plane without any stretching or tearing. In fact, if you draw any curve on your surface and measure its length, and you map it down to the plane, the length stays the same. If you have two curves on the surface and they intersect at a certain angle, and you map it down to the plane, the angle doesn't change. In geometry, we call it an isometric mapping, a mapping which does not change length and angles. And we have three basic types of developable surfaces. I do not go through the proof, but I give you a very rough sketch. So yesterday we have said a developable surface must have vanishing Gaussian curvature. This is also not a trivial statement. This is a theorem which is taken from the fact that an isometric deformation keeps the Gaussian curvature, and if you map a surface to the plane, it must have the same Gaussian curvature as the plane, which means zero. And from this, through several steps in a proof, you can conclude that your developable surface is in fact the envelope of a family of planes. And let me explain it at hand of a figure. I first do a simpler thing. We are in the plane, and we take a family, a continuous family of straight lines. I cannot draw infinitely many straight lines, but they are infinitely many, continuously changing. And then they will have an envelope, a curve which is tangent to these lines. This is a 2D thing. And now you think in 3 dimensions. You have a plane, and you continuously move your plane in 3D. It will have an envelope surface, and then this envelope surface has only a one-parameter family of tangent planes. These are the planes which you generated directly, and therefore it will have vanishing Gaussian curvature. This you can prove, and therefore it will be developable. And now it depends on how your planes move. If all your planes are, say, orthogonal to a plane, like here, to this board, then these planes will envelope a cylinder which has this curve here as a cross section. So one type of developable surface is in fact the cylinders. And once again, I repeat, I think I said it yesterday, a cylinder has an arbitrary base curve, and then it has a family of parallel straight lines. Thank you very much. Parallel straight lines. And you see, along such a straight line, we have a single tangent plane. So please note, and this is very important for the architects, do not believe if you take a straight line and you move it in space somehow, that this would be a developable surface. This is very wrong. Only in very special cases it will be developable, and these three cases are here. So one case, you move your lines that it always stays, keeps its direction, stays parallel to an initial line. This is this case, the cylinder case. The second case, all planes which you move pass through a fixed point. This means that the envelope surface is a general cone. It is formed by a family of straight lines, all of which pass through a fixed point, the vertex of the cone. And such a cone is developable. And again, along a straight line, we have a tangent plane, and this plane is tangent everywhere. Yeah, you can put it on the surface, and it really touches along the entire straight line. And the third case, this needs more discussion, because I know that the students do not like to understand it directly. It is not hard. Think, you take a space curve. Don't think of a circle. A circle already lies in a plane. Think of something which really needs 3D. Think of a helix, for example, yeah? A real space curve. And then you consider all the tangents of this space curve. So in each point of the curve you have a tangent. And this gives you all together, again, a family of straight lines. And for such a family you can prove it is always developable. Along such a straight line here, you have a constant tangent plane for this surface. So again, there is a plane which touches this surface along the entire straight line. Yeah? And this curve is a nasty curve. We will see a little later in more detail why it is a nasty curve. So you see, and this is why I just depict here this nice part, a nice part of the surface. The closer we come to this nasty thing is the worse it gets, because this is actually a singularity which is useless for applications. I will show you later. So these are the three basic types. So this should be a take-home message. Yeah, please, questions.
The first one is a special case of the...
Second one. No. These two are, in projective geometries, it would be even equivalent, because, you know, these lines also pass through a fixed point, but the point is at infinity. So these two cases are very special. You could say the following. In these two cases, these curves degenerate to a point. This is the way how you may see it. Yes, please. Today we have more questions. This is good. Yeah? Yes. No normals. Tangents. Tangent. Yeah.
How we first create the generated curve.
Arbitrary curve, yes.
Then we extrude the norm of the tangent.
Yes.
The surface is reduced.
Yes.
Okay, how can we do it vice versa?
I will tell you. Yeah. You are totally right. So this is a very good question, because it addresses a fundamental thing. You should not design a developable surface based on this curve. First of all, you don't like the curve in your application, and second, it can look very bad. So you can have a beautiful developable surface, but this curve looks, for example, like this, goes here to with a cusp, goes to infinity, comes back, and so on. It can be very bad. But we don't need this curve. We have a different approach, as you will see. Further questions? Not yet. Then let us continue. The cylinders. I think the cylinder is the most easy case to understand. And if we take, say, for example, a rectangular sheet of paper, I think everyone everybody of you can imagine how to form here a cylinder. You have a base curve and you form this cylinder. The development, I think, is pretty clear. If we have a cylinder, we can draw a curve which is orthogonal to these straight lines, meaning we intersect with a plane that is orthogonal to these lines, and such a curve which is orthogonal to the straight lines gets mapped in the unfolding to a straight line. Is this clear? Because parallel lines in the unfolding will again be parallel lines, and the intersection angle, the right intersection angle, if you have parallel lines in the plane, intersect under a right angle, so this must be a straight line. So it is clear that the development of an orthogonal cross-section of a cylinder is a straight line, and maybe even easier to understand is the following. If we take here a sequence of rectangles, we could take any planar quad, but I take here rectangles in this case, then I already have this right angle here. Then I can unfold the whole thing and get a flat sheet. This here we could call a discrete model of a cylinder. It's not smooth. It is a discrete model of a cylinder. And this is the smooth version of a cylinder. Just as a remark, if you take a right circular cylinder, you map it into the plane isometrically. You unfold it to the plane. You have to cut, of course, at first the cylinder along a straight line. Then you roll it out. If you then draw any straight line in the development, this is called the development, any straight line, and you turn it back to the cylinder, you will get a curve which is known as a helix. Yeah? A helix is generated by taking a point, rotating it about an axis, and at the same time translating it parallel to the axis. But there is a relation between rotation and translation. If you rotate about an angle, say alpha, you translate about the distance p times alpha, and this p is constant, is called the pitch of the helical motion. So this is a relation you should also know. Then, in a development, I said an orthogonal cross-section for this cylinder here, this base circle, maps to a straight line. If you take an oblique section of a right circular cylinder, you will get an ellipse, of course, yeah? And the ellipse, if you unroll it, is not a straight line anymore, right? Here you can prove it as a kind of sine curve. Yeah? If you take a cylinder which has a base circle, but the straight lines on the cylinder are not orthogonal right angle to the base, so an oblique cylinder, then if you unfold it, the base circle, again, is not mapped to a straight line because you do not have here a constant intersection angle. You have an intersection angle that varies between a right angle and some extreme angle. Yeah? So then again, this base is mapped to, in fact, also a sine curve. And a certain ellipse on this cylinder, which you get by cutting the cylinder with a plane that is orthogonal, normal, to the direction of the rulings, this section is mapped to a straight line. So such sections are mapped to straight lines. Now, to the cones. Cone is, again, simple, a discrete. Let's start with a discrete model first. We take a sequence of triangles in space which all have a fixed vertex. It's a discrete model of a cone. And we can obviously unfold this in the plane. So this is trivial, and I think we don't have to discuss it. And a cone is just a smooth limit of such a situation. So we have this cone in 3D. It is formed of straight lines, all of which pass through a fixed point, which is the vertex of the cone. And then we ask which curves to have a simple development. Yeah? Clearly, this vertex will be mapped to some point. And the straight lines will stay straight in the development. So we will get straight lines also in this development. And then you could, for example, say, if I intersect this cone with a sphere of a given radius, here I took radius capital R, I get an intersection curve. The development keeps distances. So all points of this curve have the same distance R to the vertex because they lie on this sphere of radius R. And therefore, such a curve is mapped in the development to a circle of radius R because we must have this distance R here. So here this is somehow the counterpart to these orthogonal cross-sections, and of course this sphere intersects the cone also under right angle. I hope your imagination tells you this. This is a cone case. Again, right circular cone, base circle, rotational axis of the cone, vertex on the axis. Then this base circle has the property that all its points are at a constant distance from the vertex, and therefore the base circle is mapped to a circle. However, if we intersect with another plane, for example, we get, in this case here, an ellipse. Of course, the intersection needs not always be an ellipse. You know how the cases are. And then this is an even more complicated curve we do not even discuss here. Now, this is very important because this is this discrete point of view for a general developable surface. So far we discussed the cylinders. They are very easy to understand. The cones are very easy to understand. But now we come to these tangent surfaces, and they are slightly harder to understand. And I would like to take this discrete view at first. We take a sequence of planar quadrilaterals. So like here, sequence of planar quadrilaterals. Let us look at the figure here. So we have here a planar quadrilateral, again one, and so on. And obviously, nobody will doubt that we can unfold this in the plane. Yeah? We just rotate the second plane into the first plane, and so on. Just by changing the angles from some angle to 180 degrees, it is developable. This is no doubt. And I can show you this singular curve already at this discrete model, because two consecutive planar quads meet at an edge, a straight line. So this edge, in fact, here, is the intersection line of two planes, namely the plane of the first quad and the plane of the second quad. So these two planes intersect at this straight line. Now we take a third quad. The second and the third quad also lie in a plane. I said we take planar quads. So this is a plane, and the intersection line is in this edge. Three planes intersect in a point. This means that this edge and this edge must intersect in a point. Yeah? And we continue like this. So you see, quad 1, 2, and 3 define a point. Quad 2, 3, and 4 also define a point. And obviously, the point which is defined by quads 1, 2, 3 and 2, 3, 4, these 2 points must lie on the intersection of planes 2 and 3. So they are here and here. So in this way, we generate a polyline which is exactly the discrete counterpart to the curve which I have talked about before. And as you observe that in this polyline, 2 consecutive vertices here form an edge, and this is actually this common edge here. And if you take a polyline and you connect 2 consecutive vertices, this is a discrete tangent. So this you know from high school. If you have a smooth curve and you take 2 points which are close together, you connect them, and then in a limit process, if the 2 points move together, this connecting line is moved to the tangent. So we see already that the more we refine this picture here, the thinner the quartz get, the smoother and nicer this curve will get if we do it appropriately. And this shows us that the generic developable surface will be just the tangent surface of a space curve. So this we can already see from this discrete model. Excuse me? Here?
Yeah.
Yes.
You are dividing the curvature based on the curvature degree?
There is no curvature involved.
Okay, so
You can just take any polyline. Yeah. And this gives you, yeah.
the top, distance between the points is decreasing exactly.
Here, you hear me?
Yeah.
No, this is just in this image. It can get larger, smaller. It can turn back. So this curve needs not. Yeah, this is an important remark actually. So he asks about the distribution of these curves. You cannot say so much. You can only say in the limit it will be along a smooth curve. And nasty things can happen. For example, what I've drawn here. This could also be such a curve. You are here, you come to a point, you go back, so you generate a kind of cusp here. This is possible. Many nasty things are possible. Here? Now this can also... I think this has a higher order contact with a cone than along a ruling, but this we can discuss later. But this is also good, because if this point is stationary at all, which means that it's a special case. You see already the cone as a special case. It could happen, of course, that our straight lines all pass through a fixed point. Then we do have the cone. And it could happen that all straight lines are parallel, and then we have the cylinder. So also in this discrete model, we see this these other two cases. But the most generic case, obviously, is this case. The mathematically? No, there are many strips on this surface. So if I take, I have drawn here a strip, but you could continue this surface, and I do have such a figure somewhere. Now this is just the limit process. This is not the figure. Now maybe later. Here. Let us continue here. So here I do not draw just the quartz, because I can go beyond this quartz. So here I draw this polyline, and here I draw the edge lines of the polyline. Two neighboring edge lines intersect at such a point R, a vertex of the polyline, and then we can take the entire piece here between such a wedge from here to here, or from here to here. We can take the entire thing, and here you see the nasty situation. Here you see, if you intersect this figure with a plane, this plane Q, you will get an intersection that looks like this. Here, and it goes back. So it is a cusp.
Is this important for you? You can consider isometry this surface with
Plane. Yes, sure. Yeah, sure. It is obvious, right? Same reason as before.
The curvature of this surface must be vanished.
Yes, sure.
Yeah.
Yeah, sure. Curvature is zero. Gaussian curvature is zero.
Hyperbolite.
Yes, where is not the case.
Can construct with lines by moving the line from another day.
Yeah.
Other,
This is what I said before.
Have it,
Not the curvature is negative. Yeah.
We cannot
No. Yeah.
find the isometric.
So again, you say the following. So this, if I take a straight line, and I rotate it about another straight line, which does not intersect the straight line which I'm rotating, then this point moves on a circle, and this point also moves on a circle, as I look at it roughly like this, and the whole surface which is generated is a certain hyperboloid which contains a lot of straight lines, but so like this. But it's not developable. So and you do not see this curve here on the hyperboloid. It is smooth everywhere. And if you have curvature C, we do not need curvature. If it is developable, then you do have a curve. Then these straight lines must be tangent to a curve. This is how you could also say it. Yeah? Yeah. And this curve is then a nasty curve. It looks like this. Yeah? If you intersect with a plane transversal to it. So here we can get more and more developable, obviously in this case. The more this line goes to a right angle. Because if we have a right angle, so let us discuss this example. It is very simple, but maybe useful. So if the inclination angle of this line changes, so here we get an hyperboloid like this, maybe, right? And then if we have a right angle, and we look from the top, here's our rotation axis, and here is our straight line, and we rotate about this axis, we get just the tangent surface of a circle, right? So it generates a plane. More questions here, because this is somehow, I could of course write down how you can compute this, but I would like to do it a little later because, yeah, I have a separate presentation to show this. Questions? No, then we continue here. This is what I said yesterday. Each ruling, this is called a ruling. A straight line on such a developable surface is called a ruling or a generator. So a developable surface has a continuous, in fact differentiable family of rulings or generators. Along such a ruling we have a constant tangent plane. This is extremely important. This characterizes the developability. Here we do not have a constant tangent plane. Again, you have the hyperboloid. If you take the tangent plane at this point, this is always the different. It turns around, yeah, along such a ruling. This is non-developability. And since we have a constant tangent plane, all normals have the same direction, and we take the normals, say, from the origin to get this point on the Gaussian image. The Gaussian image is a curve. This which we have said yesterday. This we do not really need. This is also useful for applications. We take two curves. Let us discuss it. We take one curve and a second curve, a curve C and a curve D. And for the moment, I make it easier for us, we take two planar curves. And we would like to construct a developable surface which connects the curve C and the curve D. So how do we go about it? By the way, I have seen implementations in CAD systems which do the following. They divide this curve into n points. They sample it n times. They sample the other curve n times, more or less arbitrarily, and then connect corresponding points. This gives you a very nice ruled surface which connects the two curves, but this ruled surface is in general not developable. You have to do the following. If you take a point here, and you are interested in the ruling through this point, or in the corresponding point on the other curve, you have to do the following. You have to consider that we want a constant tangent plane along this ruling, right? This is what the developability is characterized by. So this constant tangent plane, think of having the solution, would intersect your first plane in which the curve C lies in a tangent. Here it is. And it would intersect, likewise, the plane in which the curve D lies, also in a tangent. This means, and of course, these two tangents must meet at the intersection line of the plane which C is lying in, and the plane of D. The plane of C and the plane of D. They have this intersection line. So the construction is the following. take a point here, take the tangent, move to this intersect with this intersection line, and then from this point pass a tangent to D. Here you have maybe more options depending on how complicated this D is, and then you connect. And this you can also do here, 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 and here. Since there are cases which appear in applications more frequently, you have to connect, say, a curve with a polyline. This is also possible. But here we will have planar pieces in this connection. A plane is also a developable surface. So if we have to compute a developable surface and it contains planar sheets, it's fine. This is developable. And see, here we do the following. We have here two planes. In one plane we have this square D, and in the other plane we have this square C. And then we do the following. We take an edge of D. This is an edge of D, yeah? Of this square. Like here. We intersect it with the intersection line of the plane of the square and the plane of the circle. And then we take a tangent here, and this gives us a plane. In other words, you could also say, you take a plane passing through this edge which touches this curve. Also here you take a plane which touches this curve. The plane touches C. You could also say, I take this line, I intersect with this, but here we have parallelity, it's parallel. Then I also need to take here a parallel tangent, point with a parallel tangent. And then I get this plane. And this plane touches the curve C. This means then that the cone which I can fit in between, this is a cone, piece of a cone, will smoothly join with this plane, and it will smoothly join with this plane. You have a smooth developable surface which contains, well, here of course is not, here you have singularities. It's unavoidable, but overall it is a smooth surface. Question? This point? No, the theory says the following. I take this line, intersect with this line. This gives you a point. Here it is at infinity. It's parallel. Yeah? And then I also need to find a point here where the tangent is parallel to this. Yeah. Yeah. This is an example. You can try to do it also in a CAD system. These are more complicated examples done by an algorithm which does this. Yeah. Properties of the development, we have said. Curves on the surface and in the development have the same length. Of course, the surface area does not change, and the intersection angle does not change. I think, do not, yeah. What this is a nice image. It shows a tangent surface of a helix. You see the helix, and it shows only the lower part. There would be an upper part as well. Namely, we show here only half tangents from the curve down, and not up. This is this curve, yeah. And in the development, in fact, here it turns out if you have such a helix.
The curve is arbitrary?
Here, this curve is really done. Oh, this is not arbitrary, no. The curve down is an intersection with a plane orthogonal to the axis of the cylinder, of the helix, yeah, of the cylinder, yeah. Sure. Sure. But I showed this one. Why? Because this curve also intersects these tangents under a right angle. Now, this is easy to see. And then in the development, we also must have this right angle. And therefore, the development of this base curve is a curve which intersects the tangents of this. Yeah, this is another thing which you must prove. That the development of this curve is actually a circle. This is because a helix has constant curvature, and the curvature of this singular curve is preserved through the development operation. This one can show. So for a helix, the tangent surface of a helix, this this curve is called a regression curve. Sorry, I forgot to tell you. It's called a regression curve. This curve is mapped to a circle. The tangents are again mapped to tangents. And such a cross-section with a plane orthogonal to the helix axis is mapped to a curve which is orthogonal to the tangent. Sometimes such a curve is called an involute. I'm not sure whether you know this is two involute and evolute. Evolute is not our company. This is a thing in geometry. We were looking for a good name for this company, and together with my brother, who is a co-founder of this company, we thought about a name. And everything which really related to what we want to do was taken up. You put it into Google, done. And then he says, no, open your book. At the end, so how do you call it, the index, and you see all these geometric expressions, curvature, and so on, and I start reading evolute. And we take evolute, this looks like evolution, and so on, and so this is how we found it. Yeah? But an evolute is the following. Huh? Yeah, sure. An evolute is the following. So at least you learn something else. Yeah? We take a planar curve, and at each point we have a tangent and a normal. And then we take all these normals. These normals have an envelope, and this envelope is called the evolute. And in fact, this evolute has a meaning. So if you take the corresponding point of the evolute, we can take it here.
We call this here push up these lines.
You.
In the differential equation, we call this curve is push up this line.
Yes. You have different names. Yeah. Here, you see an evolute also. Namely, take this curve. Yeah. Then I told you in this very special case, these lines are orthogonal to the curve. So here, the evolute of the curve is a circle. And it would also mean, if you compute the curvature of this curve here, what do you have to do? You take the normal, you find the corresponding point on the evolute, and this is the curvature center. Meaning, this is the radius of curvature. So this is the radius of curvature. 1 divided by this would be the curvature. Or if you look for a circle that fits this curve at this point very well, you take your compass, you look for the corresponding point on the evolute, and here then you draw this circle. Let us do it here. Here you draw this circle. This is the midpoint. I think we have to continue. If you like, I can give you later this presentation. This is no problem. Of course, if we want to texture a surface, it is most easily done if we have a developable surface. Because we first unfold the surface in the plane, put our texture, and then map it back. There will be no distortion of the texture. Most surfaces in applications are not developable. So the computation of an appropriate mapping of such a surface into the plane, which the computer graphics guys call parametrization, is an elaborated area of research. I could tell you many things about it, but the thing is too much. It aims at computing maps to a plane which somehow minimally distort. Have minimal distortion, and then you put your texture pattern or whatever in the plane and then map it back. But I just want to make the point, for developable surfaces, obviously this is super easy. Now, this is also good. Yesterday we talked about principal curvature lines. And I remind you of the following. Principal curvature lines. We have a surface. We said at each point there are two tangent directions. One say here and one say here. which form a right angle, so this is my symbol for a right angle, which belong to the directions of extremal normal curvature. Yeah? So the surface is, say, minimally curved in this and maximal in the other direction. Of course, there are some specific points where you cannot find a minimum and a maximum because all have the same curvature. And think of a sphere. Take a point on a sphere. In each direction, you have the same curvature, obviously. And then this is not exactly well defined. But apart from such spherical points, which the differential geometers call umbilics, this is well defined, these principal directions. Everywhere on the surface, we have such a pair of orthogonal directions, tangent directions, which belong to these principal directions. And then we can say, mathematically, you integrate this system of directions, and you get a family of curves which follow always in principal direction. This is, of course, an orthogonal family of curves. Yes. Yeah. And this we call the principal curvature lines. And there are two interesting relations related to these principal curvature lines, relations to developable surfaces. And the first is depicted on the left side. So what is depicted here are these two families of principal curvature lines. And then we take at each point of a chosen principal curvature line. So we select one. A curve which always proceeds along a principal direction. At each point we have a surface normal, a line which is orthogonal to the surface. And then we have here a ruled surface, because in each point of the curve we have a surface normal. So the question is it a ruled surface like this, not developable, which is the most likely case, right? Because almost all ruled surfaces are non-developable. Or is it developable? And the interesting fact is, exactly in the case where you take a principal curvature line, this curve is developable. This surface is developable. So we can say a ruled surface formed by the normals of a surface along a curve C is developable if and only if this curve is a principal curvature line of this surface C, of this surface S. Now maybe we make an example.
I see.
Yeah.
You can design these surfaces instead of isometric transformation, conformal transformation for these surfaces. The conformal transformation preserves angles.
Yes.
You can design by planar.
Yeah, I think that's the thing is the following. If you apply a conformal transformation, a conformal map to the surface, the right angle will be preserved. But an arbitrary conformal map, I am sure, will not map them into principal curvature lines. However, if you apply special conformal maps, for example, Möbius transformations, it is well known that principal curvature lines map to principal curvature lines. Yeah, yeah. 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 The principal curvature directions. Oh, this is more complicated. I did not show you. You have to really, in this case, you have to look into a book on differential geometry. If I do this, I cannot do it in 2 lectures. Yeah? It depends a lot on how your surface is given. So maybe we discuss the most practical case is actually the case which I briefly addressed yesterday. Say you have a triangle mesh. Then you do the following. You take a local approximation of your triangle mesh by a paraboloid. I have written down yesterday slightly how to do it. Yeah? And you find it in the literature. And then you extract the principal directions from the parabola. This is a numerical estimate and nothing else. But it will do it. If you have a nice parametrization, say a spline surface, you do a very different approach. Yeah? Because then you have a parametric representation x of u and v. So, since you want to hear it, you will get it. So, to answer this question, yeah, we can do it because let me see, I don't have so much more stuff here. So let us try how far we can come. So we have a parametrization of a surface. This, you have to see it like this. You have a UV parameter plane, and you have a mapping from this parameter plane into R3. And so a point UV here is mapped to a point X, fat X of U and V here. And then this, if you move around here, you will move here on the surface. So in other words, this X of U and V is a first coordinate function, a second Y of U and V, and a third C of U and V. So this is vectorial, this X here is fat X. Yeah? Now, I think you know, if you take the partial derivative vectors with respect to U and V, so dx with respect to u, I call it simple x sub u, then you will get here a certain tangent direction, x sub u, which, by the way, is tangent to a curve along which the u varies and the v is constant. And likewise, you do a partial derivative with respect to v, x sub v. This is another tangent of your surface. So you have found the tangent plane because these two vectors, x, first partial derivative with respect to u, and partial derivative with respect to v, form the tangent plane. Then you have to take a surface normal, n equals x sub u cross x sub v, vector product, normal. This has not length 1, we make it length 1, so we divide by the norm of this vector, x sub u cross x sub v. So we do already have the Gauss map here, namely, we map a surface point x of uv to the normal n of uv. And now, to get these principal directions, yeah, we need to do the following. We think like this. We have here our surface point, and we draw a curve. How do we draw a curve on a surface? We draw a curve on a surface by drawing first a curve in the parameter domain. The curve in the parameter domain would be u of t and v of t. Right? It's a curve in the parameter domain. The tangent in the parameter domain would be the derivative here. So I call it the vector u dot, dot means derivative with respect to t, and v dot. This is a tangent vector at the parameter domain. And then the corresponding curve here is nothing else as x of u of t and v of t. You insert it. And then you do the derivative with respect to t. So let us call this c of t. And then c dot is, so you know this rule from calculus, so it is x sub u, partial derivative of x with respect to u, times u with respect to t, so u dot, which is a scalar, and therefore I put it in front. U dot xu plus v dot xv. Now, so this is this vector c dot here. Then you can also look at the Gauss image. So in the Gaussian sphere, we have here this n. And you can also insert this u of t and v of t into n, and you will get, if your point varies here along the curve, the normals will also describe a certain curve here, right? This is what we are just discussing, in fact. So we have here an n, And we do here the derivative, and we get u dot n, u plus v dot nv. Then we have a map from the tangent space here, namely where these tangent vectors lie, to the tangent space here, where the corresponding tangent vectors lie. Is this clear that these two planes are parallel? Yeah, because the normal is the same, right? Unfortunately, my drawing is bad, because this should be parallel, so really I have to repair it. This is not acceptable. Yeah, so maybe I have to repair my sphere as well. Okay, so the norm. Now, you take the following map, which is called the Weingarten map. You map u dot xu plus v dot xv onto, for some reason, minus u dot nu plus v dot nv. Yeah? And this map can be shown, that is, let's call it omega. And this map can be shown, I could show you if you like, but I think the time will not allow it, is self-adjoint. And this means it is a map from this tangent plane to this tangent plane. They are parallel. So it is nothing else. It is a linear map. It is a linear map in a two-dimensional vector space. And such a linear map, if it is self-adjoint, has two orthogonal eigenvectors and real eigenvalues. The real eigenvalues are the curvature, and the two orthogonal eigenvectors are the principal curvature directions. And the reason why I really draw it is the following. If you have found here a principal curvature direction, let's say here, if this is a principal curvature direction, the corresponding direction here will be parallel, because it's eigenvector, right? Doesn't change its direction. And this encodes the developability of this normal surface. So this surface being developable is equivalent to this parallelity here. And for computations, then I can give you some course notes also if you need, yeah, to compute these eigenvectors, but yeah, it is, yeah. Yeah. I map from the surface to the Gauss sphere. And then I take basically the derivative of the map, which is this. The derivative is a linear map, and the eigenvectors, yeah, you can really compute it like this. Yeah. Is this answered?
Yes.
Okay, thank you.
This direction, the surface, is the principal direction, these lines and these curves.
This is principal, and this is normal, surface normal.
Other principal.
The other, it would be true also for the other. It is true for both principal directions. But I draw only one here, yeah? There is a second thing. Because yesterday we discussed these strip models, yeah? If you take a principal curvature line and you form a developable surface which is tangent to your surface along this principal curvature line. So conceptually, you have to do the following. Every point here has a tangent plane, right? So along this curve, you have a smooth family, one-parameter family of tangent planes. Say envelope a developable surface. This is the surface I'm talking about. So a strip which is tangent to your surface. It turns out that the rulings, the straight lines on this developable surface are orthogonal to this curve. This is an expression of what I said yesterday also, because this direction and this direction are so-called conjugate directions. So this is a very nice case, because then the rulings are orthogonal, and if you bend it, you know, if you have such a strip, you bend it easier. But of course, be careful. The development of this strip will not be straight. So that it will be, this curve will become some curve. Yeah. Questions?
Is it possible to define a variable locally?
This is local. This is very local, because I say this is very local. It is a local property, as I see it. It is a local property. Globally, you can have things like you cannot cut it out from one sheet because in the development it would cover itself. Such things are global, but they are more nasty. Then you have to separate into pieces. Yeah?
Minimal surface, developed
No.
surface, not minimal.
Minimal surface is always having a vanishing mean curvature. Yes, and
Can I construct minimal surface in this by rules? Special case has a special condition. Minimal surface.
So, yeah.
And developed surface.
Yes. The only surface which is minimal and developable is the plane. Yeah? Yeah. Only. This does not say that you cannot make a strip model of a minimal surface. This you can do, but then it is mathematically not, then it is maybe a semi-discrete minimal. Yeah, okay. I wanted to show you the locality. Yes, so. Right. Now, how... Yeah. Yes. But ruled surface, how do we write down a ruled surface? Yeah? We have a curve L of u, L, a certain curve, and in each point of the curve we attach a straight line with a direction vector E of u, and then you can say a ruled surface X of u and v is L of u, so we go to this curve, plus along this line we take a second parameter v times E of u. Right? This is, yeah, and this is in general not developable. And to make it developable, we need a condition. And the condition turns out to be that the determinant of the derivative of L dot, or maybe L prime if you like, E and E prime is 0. This is a very local condition. Please. Here. Exactly, yeah. In a principal parametrization. So I follow principal curvature direction here. Yeah. Yeah. Then, yeah. No. Only. It is only developable if you always go in principal direction. This has nothing to do in principle with u and v, because you know a parametrization of a surface is not unique. There is infinitely many parametrizations, so you can, but you can prove there is a principal parametrization, at least locally, away from an umbilic. Yeah? Mathematician. This is, if you have a satellite shape, then for one principal direction, this surface will be on one side, and for the other principal direction, it will be on the other side. So it will be on two opposing sides. In fact, these points here on this singular curve here, so you have here a point, right? A surface normal, and then this point on the singularity. This point is a principal curvature center. It is away from this point 1 divided by the principal curvature value. And if we have a saddle shape, the principal curvatures have different signs. So the other, if I go then in the other direction, like here, this is negatively curved in fact, like here, then it would be on the other side. 1 divided by kappa 2. And in fact, you know what I show you here is not what I told you. I told you it is a smooth surface. It's not true. What I show you here is a conical mesh. In fact, what I show you here in my picture is a discrete case. This is a conical mesh. This axis here is the cone axis. The next is also the cone axis. And I told you yesterday, two adjacent cone axes lie in a plane. And so really you see a nice discrete materialization of this property. If this is a conical mesh, these neighboring cone axes are coplanar, and following along a mesh polyline in a conical mesh, I obviously get here a discrete model of a developable surface which shows a nice discrete counterpart to a theorem in a smooth setting. So it's, yeah. I think we are over time. Should we make a break and continue afterwards? Okay, thank you.